going.
Sorry, I didn't understand what we had to put in PSF.
So on the PSF, you take the PSF4.tiff. So it's one of the provided images.
Okay, thanks.
Is anybody lost and needs a little bit of help?
Yes,
yeah?
I would like to see the screen again with the things we need to put in each field.
Sorry.
So you're also in the workshop. You also have the PDF. In the workshop page on Canvas, you also have the PDF of this presentation, so you also use it. It's maybe easier if you open it on the side.
I don't know how to put convolution as an algorithm.
Yeah, the same. Good. Good that you're asking. Maybe I don't know if you are saying something, Eric, but we can't hear you.
Oh, sorry. So this is how it looks on my side. Maybe it looks different platforms, but under algorithm, if you just click the name, you can select noiseless convolution.
I don't get any of that. I just get reef and a slider that I can move from one value for reef to another value for reef.
Yeah, that's
I think
not
I remember there
expected.
was something we had to tick in from last year, some extra bit that we need to tick in to just see the stuff.
All right. Yeah, I'm sorry for that. I just reinstalled Fiji to just make sure that it worked, and yeah, it turned out like this here.
Can you share your screen?
I cannot. My computer broke down and I'm working in two different computers. In one I have the Zoom and another one I have the Fiji. So I cannot show what I'm looking at.
So how many people do not see where to put the deconvolution? Can you raise your hand? So we have Jessie and Julie. Yeah, okay, several people. I think I have, let me see. So.
You can try expanding the window maybe if it's something that is sometimes if the window's too small, everything gets cropped or some option is left out. But for me, it was at regularized inverse filter, and you just had to click that name, but it wasn't obvious that it was a button.
Yeah, looks like that. Initially. And on the previous question, which algorithm to pick, if you look at the webpage of the Convolution Lab, they have a paper where they compare all of these methods, and where the conclusion is that Richardson Lucy is the best, or that's the conclusion I draw from it at least.
Okay, I manage.
Okay, if you go, when you click on algorithm and you click on the little triangle that is on the left, Then you have regularized inverse filter. On the right side of this, there's a little arrow downwards. Then you can see all the algorithms. I can share to show you guys. So here, share. So for those who cannot see, this is the place when you open. In here, you can click that to see this. But if you click in here, you will see all the algorithms. Okay, does that solve the problem for everyone?
Yes.
Good, thank you.
Yes, but then how we can upload the images?
So how do you upload the images? Eric.
Yeah, so to upload images to the program, either you can just drag and drop them. So either you can drag the images directly where it says image in the plugin, or you can drag it to the Fiji window to open it in the Fiji. So there are two ways to do it.
Does that work for you, Horia?
No, actually, because I mean, I already opened the images in Fiji, but now if I want like to open them in this deconvolution lab too, I don't know how
Do you
to.
drag the image or?
Yeah, I drag them, but no, it doesn't work for me.
Okay, so
You can drag the file to the deconvolution lab too. Drag the file directly.
So I can show you, I can share with you, Horia. So here, sorry if I can share here, share here. So you have the file. For example, I have this one, and I've opened the I've opened the plugin. I'm going to drag it here. And then you see the path here. It's not that the file opens, it's that there's something written in here.
Okay, now I see.
Yeah?
Yeah.
Okay.
Thank you.
Is everybody on track?
Right, should I go on?
Yes, please. Yeah. Sorry.
Right. So, I mean, if you manage this despite the user interface, which is somewhat dated, you would have now two of the images I provided, and you will have one that you created on your own. And I suggest you save this as something that you recognize, for example, 2.x, piece of 4.tiff.
You are not sharing your screen?
I'm not sharing my screen. No. That's
My fault, because I stole the screen sharing from you.
Yeah, I didn't know I was kicked out. Here it is. That makes more sense. Thank you for pointing out. Okay, so this is what you should have. So you should have on the right, it's the image you created on your own. And the idea here is that if deconvolution works, you would undo this operation. So you have the image you produced, and maybe if you use this point spread function, you can deconvolve it and get back the input image. That is the question. If that would work, that would be great. So the next step then would be to take the image you created. So if you've saved it, you can drag and drop here. You would use the same PSF again, and now you can take another algorithm. for example, the pictures on Lucy. Or you can try some of the other ones if you're curious. And you would run this. And ideally, what you want to get back is this the first image with the just two spots. And if you're quick, you can do it, and you will see what you get. And if this is just yeah, inconvenient, don't worry, you can just watch, because I will show everything also, what should pop up later on. But I'll give you 1 minute to see if you can do this, because I think it's more fun if you do it yourselves.
So
Okay.
if anyone is lost, please tell us, okay? That can help.
All right. Anyone can tell us already what you get here?
I got the same two dots, but a little bit more blurry.
Yeah. Exactly. So that is what I got as well.
When you save the images, you should save them as TIFF as well, right?
Yeah, that's the best here.
Can I just ask a quick question?
Hmm?
So in the Huygens software, this one tries to estimate what you should use on your software, and the most common one that I usually get is what is called a classic maximum likelihood estimator, but I have a difficult time finding exactly what this is. And here I see that it says that Richardson Lucy is a maximum likelihood estimator. So is this the same algorithm that is used, or do you know if they use some other type of proprietary algorithms or?
Yeah, I don't know what they use. That's trade secrets, I would guess. But for sure, I think I remember that they process the images in tiles in some way. And they probably have a lot of clever tricks, having invested a lot of development time into it. And if you compare them, you will also see that Huygens is much quicker than deconvolution lab 2. And it has all these helpful features to suggest settings for you, and to take care of the PSF generation if you want, and so on. So I don't suggest that you switch from Huygens to deconvolution lab 2. It's just that it's for free and it works on all platforms, and it's fast enough to use for 2D images.
Yeah, it's just so getting a somewhat of a grasp of what I'm actually doing when I'm using this software. But is it reasonable to assume that the basic math is something similar to this Richardson Lucy?
Yes. As far as I know, it should be. Okay, well, so I'll continue here, but you can catch up later if you want. So as you saw, we don't get back the exact two spots anymore. It looks a little blurry. And this Richardson-Lucy method, it's iterative, and if you pick 25 iterations, it came this far. If you use more iterations, it should converge to the whatever the input image was originally, if there is no noise. However, the more the noise, the harder it is to converge to the right thing. And to actually deconvolve under using the perfect point spread function and no noise and so on, it's sometimes called the inverse sin, because it typically looks a little too good if you do it like that. So what we will do next is a little more interesting. So I have 4 suggestions for what you could try if you want to try something. You pick one of them that looks interesting, give you 2 minutes, and I'll show the results, the expected results from these. So you could, simplest, you could just try to increase the number of iterations and see what happens. How many do you need to get something that looks identical to the first image? You could use the wrong point spread function, because there's one which is smaller and one that is larger. You could try to do the whole thing with a larger point spread function from the beginning, or you can add noise also. And if you want to add noise, you pick another convolution algorithm. There's one that is called with noise, which adds Poissonian noise. So the noise from the light. It does not add sensor noise, I think. So pick one of these options, give it a try, and I'll discuss the outcomes in 2 minutes.
Is anyone completely lost? If you are, please tell me.
Yeah, you're supposed to be lost in a new area with this wall of text, and
It's okay. It's not. It's when you miss something, it's easy to be quite lost afterwards. But we can put you back on track. So I have that strange stuff. I don't know if it's strange or what, but that if I deconvolve the 2 dots with the PSF4, I get the perfect 2 dots. I don't get the blurry image. I'm using Richardson-Lucy and 25. Is there anything I'm doing wrong? Oh, you're muted.
yeah, if you start with the 2 dots, it's already non-blurred, right?
Okay,
It's a sharp one.
Right, but wasn't that what you wanted us to do to start with?
No, you should. Well, I'm back here. So the first was you should convolve 2 dots with the PSF4.
Right. Yes.
To
Yes.
get
Yes.
this,
Convoluted. Absolutely. That was me, not.
and then you get this with the
Yes.
2 blurry dots.
Right.
Then you would
And then
deconvolve it.
deconvolve again.
Yeah, the 2 blurry dots, the new one, by this PSF4.
Right.
And
Yes.
then you got this slightly blurry 2
Yep.
dots.
Thank you.
Okay, unless you protest, I will just continue and show what we're expected to get here. So with increasing number of iterations, it gets sharper. So 25 was what we started with. It's clear it's the slightly blurry 125 iterations, it's a little blurry. And if you go up to like 600 iterations, it looks very sharp. Very good. Just a warning, if there's noise, it will not look that nice. Then maybe you can't use that many iterations. That's something you can try. But if you use the wrong point spread function, so if you deconvolve by the slightly smaller point spread function PSF2, it doesn't really resolve the thing. It looks quite blurry. In the middle, it's the correct PSF, and to the right, it's the somewhat too large PSF. And in that case, you will probably notice, regardless of the number of iterations, that there will always be something between the dots. That's because the PSF is so large, it covers both spots. So yeah, there will be something in between. And I show this just as a precaution that it's very sensitive to the PSF. And in this case, it's just the 2D PSF, and in 3D, it's even worse. It can be. Right. And then what's the question? If you use the large PSF from the beginning, so you convolve the two spots with the PSF 8, then you get something that looks just one elongated spot. And that is something that is typically not resolved by the common definitions. However, if you deconvolve it with a lot of iteration, it actually goes to separate spots again. Now you can think of what happens if you actually have a elongated structure from the beginning. Would you get a thin elongated structure, or would you get spots? There's a slight ambiguity when it comes to the resolution limit, which is, I'd say, not trivial to neither understand or explain. I can't do it, I guess. And the last thing you could have checked is what happens if you add some noise. And if you would do that, you would see that also the output, of course, is noisy, or it doesn't look very symmetric anymore. And the more noise, the worse it gets, of course. And in all these cases, you have had the true answer all the time. But with your data, you don't know really, unless you have super resolution images to compare with or something. So yeah, to just be a little careful to draw too many conclusions from the convolution, unless you have the PSF under total control. Then I think we have 9 minutes left. So
Yes.
I'll show you just some bonus things to be also careful about. I'll start with this image. It's also from the EPFL website somewhere. You can download it. And you can deconvolve it with Deconvolution Lab 2 as well. So this be before, after deconvolution, looks fine. What happens if we would crop out a small part of this? So if we just take the upper left corner, we crop the image and then deconvolve it. Do you see the problem here? Try to see the problem. I'll show you in 5 seconds the problem if you don't see it. The problem is here. If you look close to the edge, you see that it goes completely black. Although this is a crop from a larger structure, and it doesn't go black there. And another way to look at it, so that is the lateral boundaries. Typically, with deconvolution lab 2, if you don't choose any of the boundary handling methods, you will get something that is black towards the edges. And what happens if you feed a nuclei into it? So you have some input here, and you deconvolve it in the actual in the lateral plane. It looks fine. Here in this max projection, but in the axial direction, it looks very weird, right? Because all the intensity got to the middle. That's because it goes black close to the edges. Also in 3D, so the top and bottom. So with this boundary handling, if you want to deconvolve nuclei, you need to image a little more planes before and after. Or use the padding option, because there are different padding options. I think this is with zero padding. Then we actually see that you get intensity all through the Z stack. Although it's slightly brighter at the bottom where the nuclei is a little cropped. You see here and there. And if you, now it's a complicated figure, but if you would take this input image and you would take away the bottom planes, so you have a more shallow Z stack, and then it looks like this. If you deconvolve with no padding, it's still this problem. But if you use padding now, zero padding, you see that if the nuclei was cropped in the bottom, it looks weird again. So be careful with the towards the edges, and you have to know how the software handles the edges, both axial and lateral, because it can go a little weird. And I think it close to the end. I guess Sylvie has, she threatened that you have to do this with your images. So
I'm not threatening, it's a fact.
Right, it's an invitation. Fact. Right. And if you have, so the thing is, when you go back to your lab or whatever your university, it might be that they have a license for Huygens or microevolution or some other commercial system. If they don't, and you have large volumes of images, you can also try our method, which you find on GitHub. But although it has a small graphical user interface, it's mostly a command line tool. And if you used the terminal, you might give it a try. Especially if you're on Linux, it's simple to set up. Or FreeBSD. It works on the other platforms as well. And maybe one day I'll switch to this for the workshop in the future.
Yeah, I think it's nice as well.
Yeah, and yeah, and I think we have a few more minutes. If you want, you will see later when you use the PSF generator that there are a lot of different options. If you don't know where to start with the Born and Wolf 3D optical model. It is the simplest to use because it only asks for parameters from the objective and the sensor more or less. It asks you about the refractive index, the numerical aperture, the distance between the Z planes, the emission wavelength, or or the excitation filter, the pixel size in the images, not in the detector. And then it asks you to choose a size, which is also another subject, how large PSF you need. And I would recommend that you choose odd numbers here. Default is even, but I'd say you get better results with odd numbers because then the PSF is centered on a single pixel. And always test on small crops to figure out the settings. Don't do the whole thing directly because it takes too long time, especially if you use deconvolution lab 2. I think that's all. So I wish you good luck. And if you have questions, we still have 2 more minutes.
Yes.
And if you have problems, if you want to use my software and have problems, feel free to send me an email or open an issue on GitHub also.
Yes, I would like to know first if people have been able to follow the exercises at the end, even though we had a couple of people who had no plugin. But how did it go? Did anyone not manage to do the convolution and then this different deconvolution? If you just raise your hand so I know we can chat about it afterwards. Okay, but it looks like people have managed to do this. So that's good. So you're going to have to do the same thing with your data. And there we have yeah, you can do that in 2D or in 3D, right? I mean, in this plugin, you can just download a 2D or a 3D image, right?
Yeah, it works on 2D as well.
Okay, and then you could select the Richardson Lucy anyway for both of them. I mean, I think this is what we're going to try and see if what is the impact in your images that you have. Are there any more questions for Eric?
I have a question. I'm using a single point confocal with a area scan detector, and what I recently done is tried the Zeiss new Zeiss software. There is a area scan deconvolution processing, and then because my cell have a background under some dots. And after the deconvolution, and I saw a lot of worm-like stuff in the background. I'm wondering if it is because of my background or I have too less iteration time for that.
No, it's one of those very tricky questions. It's very hard to say. I would check with another software as well, and if possible, try to query with some super resolution technique also.
Okay.
Because it is possible that the algorithms can hallucinate a little if there is a noisy background.
Okay, thank you.
But confocal is not my expertise, so I'm not sure. But in general, I wouldn't expect very big differences with confocal.
Big
Okay.
differences before and after the convolution, right?
It should look quite similar because the points by function is already so focused.
Yes. Okay, thank you.
Any more questions? Okay, well, if not, thank you very much, Eric.
Yep. Thank you all for.
And then good luck with everybody for the assignment. Okay, bye-bye.
Bye.
Oh, all right. So now we are going